Thank you. And it's, don't go over there. It's a pleasure to be here. It's my second time in Australia. Quite enjoyed the first time and definitely enjoying the second time. Pleasure to be here. Today I'm going to talk about some work that we're doing at University of Michigan on adding unlimited Watchpoint support to Linux and doing it in a way where you don't have to modify the kernel. So people that want to use applications, and I'm going to talk about some applications that can utilize this unlimited Watchpoint support. Those users don't have to modify their kernels to get access to it. All right. Is there a laser pen? This one's not working here. I'm sorry. A laser pen? Laser pointer? Laser pointer?
Pointer?
Yeah, to, put a laser point. What's the Australian word for laser pointer? Okay. If anyone's got one, oh, thank you so much. No? Okay, I'll just point and be very descriptive. Okay, thanks. So first off, let's talk about what is a watchpoint. A watchpoint is a mechanism, usually at the user level, but in this work we're going to actually put it at the kernel level, very low level, which allows you to register a callback when anybody accesses a piece of memory. And you can specify, do that callback before I access the memory, or after I access the memory, or both, as well as what type of access is it? Is it read or write, or both? So for example, if I put a pre-execution watchpoint on reads to address X in this sequence of load instructions here, when I get to the load X, right before that executes, before it modifies its destination register, I'm going to make a call out to a function, whoever declared this particular watchpoint, and I'll indicate that address X has been touched with this kind of access. Do whatever analysis you might want to do. So that's the mechanism. It's been around for a long time. You can read about data watchpoints, data breakpoints as they're sometimes called. You can read about them for many, many, many years. And there's lots of things that you can do with them. What I'm using them for is security vulnerability analysis. So I want to take just a little bit of a break from the data watchpoints implementation description and talk about the motivation for this security vulnerability analysis. So what is that? It's a way to go in and analyze a program to track what it's doing, to find and fix bugs in the program that can be potential security holes. And in order to do this, we need to be able to track memory. And so we're going to need watchpoints, many, many watchpoints, and they have to be fairly efficient if we're going to look at lots of executions of the program. So let's see why we need watchpoints to do security vulnerability analysis. Before you can understand that, let's take a look at how vulnerability analysis is done typically today. How do you find security bugs? Well, you go off and develop your program. You release your program, and users use your program. And if a lot of users use your programs, then attackers will probably get interested in that vector, in that program. And they'll attack your users, and your users will complain. And then you go debug your users' attacks. You figure out what are the bugs that are leading to these vulnerabilities, and you go back and you develop fixes for those bugs. You patch your program. That's the typical approach for vulnerability fixes today. The main problem with that is, your users are upset because you're using them as essentially a test bed for this vulnerability analysis, and developers get embarrassed on occasion when they really expose their users to some pretty heinous security holes. So a better way is security vulnerability analysis. This is where you employ technologies in the lab, technologies that are going to utilize these watchpoints, that are going to analyze the programs as they run and find these vulnerabilities before you release them to your users. So in this case, we're going to develop and debug our program just like we did before. instead of releasing it at this point, we're going to employ vulnerability analysis. I'm going to show you one of them on the next slide. These analyses are going to analyze the program as it runs, and they're going to return information about bugs in your program that you need to fix, otherwise you have a potential security hole. Then we're going to fix those bugs, or debug them, figure out what's the root cause of those, and then fix those bugs, and continue iterating around this loop until we feel we've hardened the program enough, and then release it to our customers. Now, that's better. It's not perfect. We still haven't got to the point where we can do what's called sound and complete analysis, where I can say there's no security holes in this program. That's still an intractable problem. But it's significantly better software when you take this approach. And the other advantage is it really takes the criminal out of your design cycle, which is very much a part of today's security hardening process. All right, so where do Watchpoints come into this? The vast majority of security vulnerability analysis are tracking how information comes from the outside world and flows through the computation of your program. And this is because if you look at how programs are attacked, essentially what an attacker does is it looks at your program as a black box with a bunch of knobs on it. Those knobs are the inputs, network data that you can feed to it, file information you can feed to it, options that you can feed into it. And the goal of the attacker is to find a combination of inputs which leads to a bug and allows them to derail your program, inject code in the machine, etc. All the things that attackers want to do. Now, Watchpoints are the mechanism that we're going to use to track what information inside the program is externally derived and potentially dangerous, and what what information in the program is information that was put there by the programmer, which we trust naturally. So let's take so we're going to need many Watchpoints. We don't know how much, a priori, how much of this information is externally derived, and it's better be fast if we're going to do this analysis. So let's look at the simplest analysis in this world, and that's something called, oh wait, one more point I want to make. What's really nice about security vulnerability analysis is you do not need an active attack to find and fix a security bug. So you can run your program with valid inputs that does not expose a bug, and the security analyses will come back and say, hey, there's a potential bug in line 69. Fix it. This is very powerful. You know, traditional techniques where you give it to your customer and their attack, someone has to actually craft an attack in order to find those problems. Now, because of this property, this is an area that I've been working in for a lot of years. It's a very powerful property. Also, because of this property, this is a very attractive technology in the black hat community, because it allows you to find zero-day exploits with great efficiency. Those bugs that only you know about and nobody else knows about. So it's a powerful technology. Like any powerful technologies, can be used for good or bad. All right, so let's look at the simplest kind of security vulnerability analysis and see why tracking memory efficiently is so critical to this technology. And this is called taint checking. So if you haven't had your taint checked recently, you'll see here it's pretty important to actually track this stuff. Now, what is taint? Taint is a single bit property associated with data that means it's either directly from the outside world. So when we do I/O, we're going to attach those taint bits to that data, or it's externally derived from the outside world. Now, if you're an attacker, you know, if you can find a place where someone takes something out of a network buffer and then directly indexes into an array in a dangerous fashion, great, but that's pretty rare. Often that data will get stashed away in memory, computed on, sent through a number of different functions, and then at some later point, you take that data and use it in a dangerous way. So we need to also look at what derived data in the program is derived from external sources. So we're going to have to propagate this taint through computation. If I have an add of an untainted value to a tainted value, I need a result which is tainted. So this analysis pervades much of the computation of the program when you're dealing with externally derived data. Now, those taint bits get cleared whenever you check the value. Now, what does it mean to check a value? In the context of taint analysis, it means that there's a predicate who had an input that was tainted. So, what's a predicate? A predicate is an, equal to, less than, greater than, not equal to, assert input. Any of those kind of things will clear the taint, because you'll assume in the analysis that the programmer knows what they're doing. They're actually checking this value to see its value. Now, that turns out to be a pretty naive thought, that the programmer putting the value into a predicate will actually make it safe, because most of the bugs are actually because they got the checks wrong. So the other work that I've worked on is actually full symbolic analysis of those checks to see if they're sufficiently constrained to prevent bugs. And like this, also needs this ability to track memory. So when we check the value, we'll clear the taint bits. And then anytime there's a potentially dangerous operation. So where does the rubber hit the road for the attacker? That's at array indexes, pointer dereferences, and jumps through a register. Those are the 3 points of attack in a program. When those occur, we look at those inputs to those instructions. Is there a tainted input? If there's a tainted input to one of those instructions, then that is an unchecked value doing a potentially dangerous operation. That is a point of attack of the program, and then we declare that to the program. We say, in this line, in this array access, there was an access to the array with variable x. X was derived from this input way back here, and you never checked it. Fix your program. All right. So let's take a look at an example taint analysis. Before we do that, I just want to show you what's called a data flow analysis. A little one-page short course here, Data Flow Analysis 101. I've got this piece of code over here on the left. It's going to read some input from the outside world, and it's going to do a bunch of computation on it. Now, when I do security vulnerability analysis, I'm not so concerned about the order of the code. I'm concerned about the flow of the information through the program and how it's used. So I actually build a different construct to represent the activities of the program, and that's called a data flow graph. So when I read my input X, I create an input from I/O, and I get this node in the graph, which is the creation of this value X. When I then compute on X, multiply times 1024 and produce Y, I get a new node in the data flow graph, which is a child of this previous line of code, which says that the output of that goes to the input of this next computation. So I'm flowing the I/O through that computation, then through this computation. And the next line of code then flows that to the next point. This next line of code is derived off this earlier one. So you can see how this tracks programmatically the flow of information through your program. That's the goal of a data flow analysis. And we can build these on the fly as the program runs and analyze at any particular point in the program for every input of this instruction or this line of code. Is that externally derived data? And if it is, where did it come from? Or is it internal program data that we can trust from the programmer? So continuing on here, y++ derived from this computation of y, and this computation of z from that earlier computation of x. Now when I do taint checking, I'm going to build this graph on the fly, and I'm going to propagate those taint bits through the data flow graph. So let's see our example here again. I take my input, I read this value of x. Now I need to attach that taint bit. Now in security vulnerability analysis, we call this metadata. And different analyses will attach different kinds of metadata onto it. So we're going to attach a metadata that says, yeah, that's tainted. That green box there, this is tainted information. And I'm going to propagate that tainted information through these different computations. Now let's say there's some point in the program where I see this computation X goes through a check, some sort of validation. Then I clear the taint on that point, and then that subgraph is all safe computation. So when I finally do my checks here at these computations, I'll say, these are unsafe here because this is tainted data, and this is a safe value here because it got validated. Now, the reason I need watchpoints is because I'm going to use watchpoints to propagate my taint data through memory. And I want to watch any storage that's tainted. If it gets touched, I want to know about it, and I want to propagate the results based on the rules of the analysis. In the case of taint checking, if I touch an input, if I read a tainted value, and it goes into a computation, I want to then write a tainted output and watch that new piece of data. Now, how many things do I need to watch? Totally depends on your program. Some programs, don't generate very much tainted information at all. Other programs like gzip pipe a network input into gzip, and every computation is tainted. All right, so before I leave this, I just want to insert my gratuitous plug here. Tomorrow at 1:20, I'm giving a security tutorial related to this work, but just a plain tutorial. We're going to learn the basics of computer security threats and protections. We're going to look at open source tools that you can use today to help build more secure software, including taint checking and a variety of other analyses. So please come to that, and you'll be surprised how much you can learn about security in 1.83 repeating hours tomorrow, please. All right, so back to this presentation here. So that was taint checking, which is a security analysis, vulnerability analysis that can utilize Watchpoints. But Watchpoints are really generally useful across a broad array of applications. I've just listed some of them here. Program debugging. GDB lets you put Watchpoints on a variable. You can say, watch this variable. If it changes, stop the program and tell me about it. Bounds checking. We can do something called canary-based bound checking, where whenever you have an array, you put data at the end of it that you want to watch. If anybody touches this data, it's called the canary, tell me about it. That means you overflowed a buffer, another popular attack in the security world. Data race detection. If you have a parallel threaded program and you want to determine if your program has proper locks on it, that there aren't communications between the threads that are not properly locked, you can do an analysis called happens before, which requires that you identify shared data and then look at the order of accesses to it. Watchpoints, fantastic for that kind of analysis. You can find some really great bugs in parallel programs. Deterministic execution is another popular optimization in the parallel world that allows you to fix the way a parallel program runs so that it's deterministic and easily debugged. You need Watchpoints for that. Speculative program optimizations, a variety of compiler optimizations that write values assuming they're not going to be touched by other parts of the program. Because, for example, it's a value that's pointed to by another thread, and we don't know if that thread's going to touch that value. So you execute your program assuming it won't be touched. You place Watchpoints on that data, and if it is touched, you revert to a less optimized version of your program. As long as you don't do that very often, you can get huge speed-ups. Checkpoint and rollback support. If you want to make a checkpoint, put watch on all the data at the point of the checkpoint. Anybody touches some of that data, put it into a log, a revision log, so that you can know all the changes that happen to your checkpoint. Semi-space garbage collection, a way to put data into different spaces and do garbage collection on it. We have to monitor that data. Hybrid transactional memory. It's a popular style of parallel programming that allows you to execute program essentially without locks and then merge the changes in together, and that merging process can use these Watchpoints. So a generally very useful mechanism. Now, the more efficient it is and the more we have of them, the more capabilities we can get. So I've kind of ordered these in rough order of how many Watchpoints you need and how efficient they must be. And because Watchpoints are so inefficient today, probably the only thing you know about on this list is the first one that only needs a few Watchpoints and they don't have to be very efficient. So that's a case for Watchpoints. How do we implement Watchpoints? Let's take a look at how they're implemented today. And most systems do support Watchpoints today. And they're typically implemented in hardware using debug registers. Most popular way. Now, the advantage of hardware debug registers, which will track access to a particular storage, is very fast. There's no slowdown at all in your program when you're using data breakpoints or Watchpoints. The disadvantages is very few. Here I've listed in this table for a number of different architectures how many Watchpoints you get. And many of them are 1, in the best case 16. Now that's pretty limiting. And it's really difficult to virtualize this kind of resource because you don't know in advance which load and store is going to touch a particular piece of data. Every single load or store potentially has to be instrumented to do that. So really, it's a very limited resource, and it's really typically only used by programs like GDB, where you can set, if you ask GDB how many watch points you can set, it'll tell you how many hardware watch points your hardware supports. They're also limited size, right? What if I want to watch an entire array? I can't do that with this. And also, they're unaware of threads. What if I'm only concerned about the communication or the updates of this thread on that data? For example, if I want to do data race detection, thread A can touch this data all at once. It's if thread B, C, D, any of the other threads touch that I'm concerned about. So that these facilities are not multi-threading aware. So other techniques that are more flexible, for example, Valgrind uses binary instrumentation. Every single load and store is replaced with a load and store that first checks the watch points to see if there's anything that it's going to touch. The advantage is you get unlimited watch points. So now you can see there's taint checking tools available on the Valgrind platform. You get unlimited size. You can watch entire arrays. You can implement all kinds of facilities there. The disadvantage is slow, really slow, because now what used to be a 2-cycle load is a 5,000 cycle load. And since every third instruction is a load, your program is going to run hundreds to thousands of times slower. It's also completely non-portable, too, because your instrumentation is with respect to an underlying instruction set. So if you want to move this from x86 to ARM, you got a lot of work ahead of you. So a more portable technique is mprotect. This is what Electric Fence uses, for example. The idea here is to use an underlying user-level memory protection capability to basically turn off accesses to the pages that you have watch points in. And then if someone touches it, checks to see if that's an access to my watch point. Now, the advantage is here, again, you can do unlimited watch points, unlimited size, and it's portable. The downside is it is extremely slow, significantly slower than program instrumentation, because now we are invoking privilege changes, we're going in and out of kernel multiple times, we're doing things that are not very efficient on modern systems. Also, you can't watch the kernel, which is a downside if you want to do watch points in the kernel. Now, the baseline approach we use, that we optimize, for example, it's the baseline approach is implemented in Solaris, is VM watch points. What this is you use the virtual memory system to implement your watch points by essentially making pages that have watch points on them inaccessible, and then overloading the page fault capability to first check is it inaccessible because I'm watching data on this page, or is it inaccessible because it's out to swap. It's on the swap. So again, we got unlimited watch points, unlimited size. It's very portable, but it can be very slow. And the reason why it can be very slow is you can get a lot of false positives. If you touch a page, if you touch memory on the page that you're not watching, you're still going to take this page fault. And so let's dig down into this VM-based watch point implementation and see why it's so inefficient when there are data on the page that isn't being watched that's being touched. So here we've got my virtual memory system. I've got a bunch of 4K pages there in my virtual memory system, and I'm going to set up watch points. Over the course of executing my analysis, the blue stuff is stuff that I'm watching. Variable amounts of stuff in each page. Some pages don't have anything, and I can have as many things watched as I want. Now, when I access pages without watch points, those two in they're full speed, no change. The downside of this approach is pages that have any watch points in them are marked not present. Even if they are resident in memory, they're not out on swap. They're marked not present in the virtual memory system, so that I get an indication that someone touched the page that's being watched. So now when I access one of the pages that has a watch point in it, I've got to do some special handling in the fault handler. the page file handler. The first thing I'm going to do is I'm going to check the metadata associated with the page. So I'm going to associate with every page that has watch points on it some extra data in the virtual memory system, the metadata. That will indicate what part of memory is being watched. And I'm going to see, did I touch one of those watched addresses? If yes, I'm going to invoke the callback function. Now, regardless of whether or not I invoke the callback function, I'm going to do the next line, which is really slow. And that's why we pay when you touch data that isn't watched. Well, we've got to actually access the data. So the first thing I need to do is I need to turn the page as present, if it is resident. Now that requires a TLB shoot down. That requires a transition in the operating system. Expensive, expensive. Then I'm going to single step my machine. I only want one instruction to execute because I don't want to continue executing with this page with watch data in a present state. I got to let that one instruction execute, and then I got to turn the page back to not present so that if future instructions access that data, I get an indication again. So I single step one instruction, then I remark the page not present, again, another TLB shoot down, another transition in the operating system, and resume execution. So you can see to execute that every time I touch a page, I'm going into the operating system multiple times, I'm shooting down my TLB multiple times, and then I'm resuming execution. Even when I touch things that aren't watched. Question?
How come you have another thread going around?
Wait, I didn't hear that.
You need to stop the other thread as well.
Indeed, I need to stop the threads that are on the same piece of hardware. Now, depending on whether or not the other threads I'm watching their data, I would have to stop them as well. Yeah. In essence, what I need to have some sort of atomicity on those accesses to my metadata and the invoking of my callbacks. Yeah. Okay. So the big problem here is that single step and all those turning on and off of the present bits is extremely expensive, even when you're accessing data that isn't watched. So a powerful technique, but thanks. Powerful technique, but not particularly fast. So let's go into the fast kernel VM work that we did. And three things, really three goals we tried to achieve here. One was no kernel modifications. In the past, it's been my experience that when you want to deploy anything that requires a kernel modification, it will only be deployed in your own lab. People don't want to mod their kernels. It's like a huge barrier to getting anything, to get users, in our case, people using user-level programs to use your facility. So we need to change the page fault semantics without modding the kernel. That's a challenge. Second, we need a place to stash all that underlying data that we've got. And then third, we need to address the cost of those false positives that I just talked about. So let's see how we're going to do that. First, we're going to use a loadable kernel module, LKM. So there's the ability to load a module into the kernel. The second challenge is how do you hook into the virtual memory system without changing the virtual memory system, which is part of the kernel. And the way we did that is using the kprobes facility, which is a very useful performance analysis facility in the kernel that allows you to watch when kernel functions are invoked. But we used it to actually manipulate the semantics of the page fault handlers. So we got the ability to do stuff before the page fault handler executes and something after the page fault handler executes. And it does this with trampolines. So we can't really get into the middle of the functions, but if we can do our work before and after, boom, kprobes work. Now, how do we get information into our system calls that we're adding? Because we need a facility at the user level to define these new functions. We're doing that through the proc file system. So there's essentially a proc node, which is the new system call, and when you write to it information, it puts in and takes out these data watch points. Now currently, one of the challenges we have is implementing security on this facility, so we only allow you to do this if you're root. And then the output, the way we get information back, is in the function call of the invoked callback. That'll tell you all the information of what happened and who did what. All right, so that's our way to extend the kernel. without changing the underlying, without patching it, here's how we can store this extra data, right? We can't store our data into the virtual memory structures in the kernel. We need to somehow extend those structures. So what we did is we basically defined our own data structure for metadata and then index it with mmstruct, the pointer to mmstruct, which is the page table information that we were extending. So you go to mmstruct and you index into that with an address. You can take the mmstruct address, find our metadata, and index into that with our address. So we can attach all of our data on the fly. Now this data stays resident regardless if the page is swapped in or swapped out, because we don't extend the swap system. Extending that would be just a really bit of a big barrier. So the cost in our world of not having to extend the swap system to store our metadata is you just need a lot of physical RAM, the worst case amount of physical RAM to hold all your metadata. And then the way we reclaim this information is we have a Reaper thread in the kernel which looks for processes that have gone away and their mmstructs are no longer allocated, and then reclaims that metadata. So a fairly efficient and straightforward way to extend those internal structures without patching the kernel. Now we need to also store a little bit of information in the page tables. Fortunately on x86, Intel's given us a little bit of breathing room there, and we're able to encode in 2 bits of a PAE, physical address extension style page table entry, whether or not the page, if there's no access to the page, we can differentiate in the kernel whether it's no access because it's no access, maybe mprotect made it no access, or it's no access because it's watched, or it's watched and no access. That's the case where mprotect and the kernel level watch code are both interested in the page. So one thing we do is we do live cleanly with mprotect facility. All right, now the third thing is we want to address the cost of those false positives. And that cost is because every time you touch a piece of memory on a watch page, you have to shoot down your TLB, set things back to present, and then you have to single step an instruction, and then you got to shoot down your TLB as you set it to not present, and then continue to execute. The solution we found here was just emulate the instruction. Don't go back out into the processor and do 2 TLB shoot downs and 2 user to kernel transitions. Just implement an emulator, like QEMU or whatever. We implemented our own tiny little emulator which says, what is the next instruction? It's a load. I'll implement that. Thanks. So that really saves a lot of time. I'll show you that in a minute. But here's a summary of what we're doing in this page file handler. So when the page file handler is invoked, we have a pre-handler which goes in and looks to see whether or not the page is watched. If it's not watched, it just goes back into the page file handler. If it is watched, it goes into the post handler, and if it's not present, it goes and swaps it back in. And then after it swaps it back in, it goes into the post handler. What does the post handler do? It says, hey, is that the address that you're touching actually a watched address? If it is, then we're going to invoke the callback, and then afterwards we're going to emulate the instruction. So fairly straightforward extensions implemented as both a pre-handler and a post-handler to the page fault routines, and we insert those using kprobes facility. So let's do some performance analysis. Let's take a look at how fast it is. The way we did that is we looked at 3 different implementations of unlimited watch points. The first is our one that I described in this presentation today, fast kernel watch points with emulation. Then we did also one without emulation where we make those multiple trips back and in and out of the operating system with a single step. And then we did a mprotect based watch point implementation. And the way that worked is shown in this figure here. Now one of the challenges with using mprotect to implement unlimited watch points is you can't single step yourself in Linux. It's kind of a shortcoming in that facility. So you need to have somebody else watch you. So it's a true process solution where mprotect will mark pages in the other process that have watch data on them as inaccessible. That'll send signals back to this application. which we can use ptrace to signal step this application. That'll send signals back when it's done, and then we can update those mprotects and continue running. So the same basic mechanism I discussed before, but using mprotect from a second process or thread. And so here's the performance. Now this is worst case performance. This is every single access is to a page that is watched, but without watch data. So this is the worst case slowdown that you could experience for this kind of technology. And this is a log scale. So mprotect based Watchpoints slow the program down about 100,000 times. Fast kernel without emulation slows down the program about 1,000 times if every access is to a watched page but not watched data. And then the fast kernel with emulation is about 300 times slower in the worst case. So it's a factor of 3 improvement in the performance of the system with that emulation. So pretty big win there. Now, actual slowdowns really depend on your underlying on the application that's used in the facility. But you can expect for most applications that the Watchpoint facility is going to be on the order of 50% to 400% overhead. It's sizable. This is not something you would deploy to customers. It's still a pretty slow facility. So just one more plug here. I'll tell you a little bit about some of the work I'm doing in the Testudo project is how do we take these slow facilities and distribute them widely? And the solution is really sampling. We don't want to do analysis on everything all the time. We want to use this facility that has this overhead that can be great. It can be improved with work like this, but it is a great overhead, and we want to only invoke it in the minimal number of times to meet the overhead requirements that users will tolerate. So you take a program that's instrumented but sampled, and you run it, because it's sampled, you run it on many, many machines. And they randomly choose things to analyze. In the case of taint analysis, they would randomly pick paths of analysis. And if they ever find any problems, they just phone home to the developers. So even with high overheads, you can get these analyses into the hands of users, and ultimately that's where you get the best amount of analysis and testing, when users actually use. Developers don't always know what users are going to do with their code, and so getting users to run those tests for you is really the ideal case. So frustration is subsiding, still not a full, complete solution, still not fully testing stuff, but doing better all the time. So to conclude, Fast Unlimited Watchpoints is a great technology that really supports a lot of program analysis for security and many other applications. I think it's worthwhile to put resources into this and to really make Linux a platform of choice for this kind of analysis. Fast kernel Watchpoints in Linux, what we've been working on is a facility that provides better performance and flexibility than what's been possible previously. It's implemented as a loadable kernel module, very easy to add it to your system, doesn't require patching. It utilizes the VM system to watch pages that have watch data on them, and then optimizes the case when you touch a page with data that is not watched by emulating those instructions. And there's an experimental release. If you go to this page right now, I promise tonight I'll put this, it just says TBD, but I'll put it on tonight. Experimental release. Now, what does experimental release mean? It means this is a potentially buggy piece of code running in your kernel, buyer beware, right? It could mess you up bad. But we're continuing to work on it and doing a number of things, trying to improve the stability of this. We're trying to really come up with a great permission solution, something along the lines of ptrace, the way it uses it. We're doing a GDB port that allow unlimited Watchpoints efficiently in GDB. So after your 4th Watchpoint, it won't say no more. Better emulation capability and large page support. So continue to work on this, and also interested in other people that want to use this for a potential application or contribute to this as well. And then some acknowledgments. This is joint work with Valery Bertacco, also at University of Michigan, and Seth Petty. And then my PhD students have been working on this as well, Joe, Hungy, David, and Nixon. So thank you very much. Happy to take questions.
Okay, has anybody got any questions for Todd? So when you put that in production, what's the ratio of false warnings to useful stuff? Is it 1%, 50%?
It totally depends on the application. Now, some applications, like, well, a good example is any kind of application with compression or encryption, the false positive rate would be very low. A database application, on the other hand, with very small nodes in the in-memory database, the amount of false positives could be very high. And that's really why we're really focusing on a sample-based approach, because if you can take your application to a sampling-based approach, if your false positive rate gets high, you can essentially eliminate data on pages that have a lot of data that isn't watched, but is causing you slowdown in that case. So you essentially say, yeah, I can only watch one piece of data on this page, or I can't watch any at all. So it can potentially be very bad, and so you need a mechanism to get rid of that data.
For the x86 case, if you thought of actually falling back to real watch points, if a page is getting a lot of hot, false positives, and using one of the real watch points in that case.
Yes. Excellent point. Now, I'll just put a plug in for some other work we're doing. So one of the things, so my background is in computer architecture. One of the things we've really been focused on is how do you meld hardware resources with software resources? And we've got a paper coming up in ASPOS, Architectural Support for Programming Languages and Operating Systems, which does just that. And one of the things it does is it says, if I have a page that has a very little amount of data that's being watched, and I have those hardware debug resources available, I'm going to utilize that. Also in that paper, we talk about a couple of other very simple hardware resources that could be added that would scoop up a massive amount of the VM-based stuff. One thing that would be very useful is something called a range cache. Something that could just hold 4 to 16 ranges of data that's being watched. That scoops up about half of all of your VM work. And when you have those facilities, then it really becomes much more efficient, much less false positives. And one of the reasons why we're really focused on all the applications that can use watch points is because we want to make a case for hardware manufacturers, put some of this stuff into your hardware because it'll be really useful to many communities. Yes.
Any more questions?
Yes.
I didn't quite understand how you work out the taint. I didn't understand how you work out which data needs to be associated with the taint bits. And is this, you've written some software to analyze the code and work out which bits are coming from outside, and it's a kind of, does this require access to the source code to do this, or you can analyze the behavior of the executable, or what's the way you get the taint points? I'm sorry, I didn't understand.
There's a variety of mechanisms. Though in our work, the way we taint information is we put it in the Zen hypervisor. And what's great about Zen is it gives you callbacks when anyone tries to do I/O for the purpose of virtualizing that I/O. But in our case, we just wanted to add taint information to the I/O data. So we could easily watch when any access to I/O occurred and then attach that metadata. Now you can do it at the program level. There's tools that do taint tracking at the source code level. And essentially what they do is they put wrappers on system calls that add taint information when you do an F-read, for example, to that buffer. And then the compiler will put the instrumentation in the code to actually propagate that information. And you can do it in managed languages. For example, Perl. There's a version of Perl called Taint Perl, which implements in the virtual machine of Perl this taint tracking. So that, as you're reading from system calls, it attaches the taint information to that data, and as it propagates through the system, it gives you warnings when you do potentially dangerous things. In the case of a managed language, it's not an array access, it's actually using that data to access the file system or to do an external communication. So you're manipulating the program that way. So it can be really done at any level.
So that using the compiler to add the information, that requires A specially modified compiler.
Yeah.
Has anyone done that?
Oh, yeah. So come to my tutorial tomorrow. We'll look at Valgrind. The Valgrind platform has a tool which does that. It does that through the Valgrind binary instrumentation platform. So yeah, there's a variety of solutions that do that. OpenBSD doesn't do taint analysis, but it does instrumentation on every piece of code it generates by default. And so there are facilities out there that do this kind of analysis. Yes?
Have you considered making your lives a lot easier by submitting some of that upstream, which means you no longer need all of your hacks to work around and be in kernel in the first place?
Yeah, well, so the first time we did this, we put it in the kernel. Right, and then the next barrier is to get it into the kernel proper and then back out in the kernel. And we got chicken. That seemed a little bit too daunting for us because we're not really OS developers. We're hardware people that do low-level software. And so instead we decided to go the loadable kernel module approach. And I've been really happy with that approach. Our only requirement for your underlying system is that you're running PAE, which is the extended page tables on x86, and that you've got a version of the Linux kernel that supports kprobes. That's pretty much everybody running on x86 that's been bought in the last 5 years. So it seemed like a good solution that didn't require an external buy-in to get our facility out. Now, one of the things in the testudo work, we want to build a LAMP stack that we can distribute to people that will do analysis, in the field. And if that required a kernel patch or waiting for it to get into the kernel, that's really a big problem for me. So yeah, that's why we decided not to go that route.
Okay, I'm afraid that's all we have time for today. On behalf of the conference team, I would like to say thank you very much for your presentation today.
Thank you.
Can I get a round of applause, thanks?